Hi! Well, thanks for taking the practice exam. We're going to quickly go through the problems in a couple of minutes. But before we do, I just want to give a couple pieces of advice. This shouldn't surprise you. I often give advice. Occasionally it has been good. So, when you're taking the test, pay attention and read it carefully. There's a tendency sometimes to not pay attention, and you might notice that we maybe have a slightly different order that we write things in than normally, or maybe there's something which is a multiple selection problem and there might be more than one correct answer. Read the prompts carefully. Related to that is work to eliminate options. A multiple choice test is different than the kind of test we've done in the past. You don't have to show all your steps. You just have to do enough to be able to get to an answer. And one way to get to an answer is to say, well, let me eliminate other possibilities. And so if you can work to eliminate the other possibilities, that helps. There's a lot of time to take the test. We recommend you start early if possible and get it done. I know it looks like it says get it cloned, but that doesn't make any sense. No, get it done. And just don't have this hanging over you all day. You should just get it out of the way and be free. And don't panic. And I understand the test is stressful. That's why we want you to start it early. So if you need to take a break, get up from your computer and walk around for a couple minutes, you can do it. If you need to go scream into a pillow, get a drink of water, use the restroom, okay, that's fine. Don't panic. And remember, we do love you. Now, that isn't to say we're not going to challenge you, because we always challenge the people that we love. You might have experienced that in the last couple of weeks, that some of the biggest challenges have come from your loved ones. But we want you to succeed. We're not going to punish you. See, there's a difference between being challenged and being punished. We're here to challenge you. And that means that we believe in fairness. We're going to give you a fair test, and we're going to let you have an opportunity to demonstrate what you've learned. And we hope that you've learned something. All right. Well, with that out of the way, we can begin. All right. We'll start with the first problem. And we'll try to go through this a little bit faster than we normally would because, well, it's multiple choice. And don't worry, there's plenty of problems. So we'll be here for a while. Okay. Got to enjoy it, right? It's our last hurrah. So we're doing a partial fraction decomposition of x minus 1 over x times x squared plus x times x squared plus 1. Now, of course, if we're doing partial fractions, the first thing we make sure have we factored our denominator. Because it looks like they factored it, but did they factor it all the way? Because remember, we need to go all the way. They seem a little bit suspicious there. X squared plus x. See, I could factor an x out. So this is really x minus 1 over x squared times x plus 1 times x squared plus 1. Which means, okay, what should we have? Well, we should have the x squared says, look, I should have something over x squared, because you will work your way up. Then you have your x plus 1, and then you have your x squared plus 1. Now, what goes in the upstairs? Well, some constant, and the x squared plus 1 versus the x squared. This is an irreducible. Here, we're just working with powers. This will have dx plus e. So, let's see. This one's not right because, see, it's missing that over x. You have to work your way up. This one, we haven't factored at x squared plus x. Okay, so that's not right. So, okay, well, what about this? A over x, something over x squared. It doesn't matter what order, so that's okay. B over x plus 1. Yeah, yep, okay, that's good. How about this last one? What's wrong? Well, here, it's this last term. It isn't dx plus e, it's just the d. And so that's wrong too. All right, so the answer is C. Now, one of the things you might want to do is starting to get in the habit of, can we eliminate things early? Because oftentimes, we can sometimes solve the problem without much work if we think about what must be true. So here's a fun fact. Look at your degree here. The denominator, what is it? It's degree 5. Well, whatever the degree is, that's how many pieces you don't know. See, A, B, C, D, E, that's 5 things. So that says this term and this one can be eliminated automatically because you're missing a 5th piece. It should have 5 unknowns, it only has 4. And then once you eliminate those, you can say, well, look, that's not factored, so that can't be true either. And now you've eliminated everything but C. So oftentimes, if you think about it, say what must be true, you can save yourself time. All right. And time is nice to have. Number 2, consider the series. We have x minus 3 to the power 2n over n times 9 to the n. Which of the following x values are in the interval of convergence? And select all that apply. Now, one thing we can do is we can just sort of quickly scan. We can try to figure things out, or we can just sort of say, well, what must be true? One thing that must be true is we need to start at 1, because if you start at 0, whoa, lots of problems. Okay, we'll fix that in post-production. All right, when you plug in 3, 3 minus 3 is 0, and once you have 0, you're going to be good to go. So life is good for 3. How about 6? Well, 6 minus 3 is 3. 3 to the 2n is 9 to the n. 9 to the n over 9 to the n cancel. And you get 1 over n. That diverges. Now, here, what do we see? We know at 3, we're good to go. Because, in fact, that's the center. At 6, we said we're diverging, which means everything after 6 is going to diverge as well. So we can roll out 9. Now, what we can do is we can also go in the other direction. See, 0. 0 is, if I go 3 to 6, 3 coming over here, well, how about 0? What's true? 0 minus 3 to the 2n. Well, that's negative 3 to the 2n, which again is the same as 9 to the n, because negative 3 squared is 9. 9 to the n's cancel, 1 over n. Again, 0 doesn't work, which means everything below 0 is out. So that rules everything there, which means we're down to just one more possible case, which is 2. And what do you get? Well, when you plug in 2, you're going to get the sum of 2 minus 3 to the power 2n over n times 9 to the n. But 2 minus 3 is negative 1 to the power 2n. So really that's the sum of 1 over n times 9 to the n. And that 9 to the n is so big, it definitely makes the terms get small. That's going to converge, and we're good. Now, another thing we could do is work through things like the interval of convergence, radius of convergence. But sometimes it takes just as much work to fully do that process. It's just a sort of spot and check. Now, keep in mind, we are not going to check your work. So this is to your advantage. You can say, well, let's just sort of pick things and identify how can I quickly rule things out. And you don't have to be really clean about your work here. You just need to be clean enough to make sure you're doing it correctly. Number 3. Find the limit of the sequence where it's 1, 1 plus 1 over 1, 1 plus 1 over 1 plus 1 over 1, 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, ... Now what happens? Well, this is defined by the first term is 1, and then the next term, you take 1 plus 1 over your previous term. All right, well, what must be true? Well, we can rule some things out pretty quickly. So, for instance, if it's a limit, you can't have multiple correct answers. So that's out. Notice we're always going to have 1 plus something, so that's out. 1 minus root 5, well, root 5 is like 2 point something. That's a negative value. No way that can be true. If it's 1 plus something, unless it's 1 plus 0, which it won't be. And so just without really doing anything other than thinking, okay, limits have to be unique, have to be at least as big as 1, and should be bigger than 1, we get to the conclusion that there's only one viable candidate. All right, So that's the answer. Wow, that was quick. What if we were to do it properly? What would we say? Well, look, we're looking for the limit, right? So this is going to L. So this is the limit. So what do we get? We get L should be, because remember, a sub n is getting close to L. 1 plus 1 over L. And again, that's a sub n minus 1 is getting close to L. So essentially you're saying in the long run, what's happening? Whatever it goes to has to satisfy this relationship. Well, get rid of your denominator. Don't want a fraction if you can help it. L squared equals L plus 1. L squared minus L minus 1 equals 0. This is one of those rare times where Pythagorean theorem, sorry, it's not Pythagorean theorem, quadratic formula has to be used. Oh, why am I thinking Pythagorean theorem? It's been a long semester, right? All right, negative b plus or minus square root b squared minus 4ac all over 2a, which is 1 plus or minus square root of 5 over 2. So that gets us to two possibilities, 1 plus square root of 5 over 2, 1 minus square root of 5 over 2. But, as we noted before, that's negative. You can eliminate that, and there's our answer. So you can do things in multiple different ways. All right. Number 4. What is the exact value? Ooh, exact value. All right. Now, whenever we're asked to find an exact value or find a value, it really says you're looking for one of three things: geometric, or telescoping, or you're hoping, if those two fail, we're going to do something with Taylor. Well, we can see pretty much everything has powers of n. So that's geometric. Now, let's see. What can we do? Well, the nice thing is there's a plus sign up here. Plus in the numerator, that's a good kind of plus. So that's the sum, n equals 0 to infinity, of 3n over 7 to the n plus 1, plus the sum, n equals 0 to infinity, of 2n over 7 to the n plus 1. Now, I really want to get this as something to the n, because right now, we're almost there. The plus 1, though, that's messy. Well, there's ways to fix that. So we're going to take the plus 1. That means we have a 7. I'll pull it out. And again, I'll take off this plus 1 and put a 7th out in front. So what we really have is 1/7 the sum of 3/7 to the n, and 1/7 the sum 2/7 to the n. All right, well, good, perfect, right? So 1/7. Now the first term, n equals 0. We always plug in the first term because that's what goes in the top. So our first term is 1 over 1 minus, and then the ratio 3/7. Because the ratio, that's that r you're multiplying by. 1/7, and again, plug in 0. Something to the 0 is 1. So that goes upstairs. Remember, this is the first term in your series. 1 minus 2/7. Now, you can multiply the 7 in. So that becomes 1 over 7 minus 3 plus 1 over 7 minus 2. Or, if you like, that's really 1 over 4 plus 1 over 5. That's looking promising. Common denominator would be 20. So that's 5 over 20 plus 4 over 20, which gets us to 9 over 20. And that's it. There's our answer. Woohoo! Good. So yeah, one of the things that's it's nice to be able to do is learn how to spot things, because that saves us a lot of work. And so if we can learn to recognize, oh, powers of n, that's geometric, life is good. And we like it when life is good. It's much better than the alternative. Number 5, Gene Simmons. So this is apparently a rock star. Okay, he weighs 210 pounds and is to be lifted 30 feet into the air on a platform weighing 40 pounds by a chain attached to a pulley 60 feet in the air. All right, so let's see. Oftentimes it helps to draw pictures. So here's our little pulley. And there's a chain coming down here, and we'll put a little basket here because, you know, safety first. If you're a rock star, they're well known to be people who firmly believe in following safety and health guidelines. All right, so here's our Mr. Simmons here. All right, now, and he weighs 210 pounds. And, okay, so there's our ground. And what do we know? Well, we know this distance here is 60 feet. And the chain weighs 10 pounds per foot. And the last thing is, of course, we're not going all the way. We're going to move up 30 feet. All right, so there's our picture. Now, what do we need to do? Well, when we're talking about work, the way we do work is we integrate force. Because essentially what you're doing is really adding up all the little bits of, you know, move them just a little tiny bit. So the question is, suppose, well, let's let x be the height up. So, for example, here we'll have x equals 0, and we want to go up to x equals 30. Okay, now the question is, what's the weight at a particular value for x? Well, so if I'm here at some arbitrary value of x, I have three things. I have the weight of the Simmons, that's 210. The weight of the basket, the platform, that's 40. And the weight of the chain. Now the chain is all the way up to where the pulley is. So the distance is 60 minus x. That's the distance. How do I get the weight? I multiply that by 10. So that's 210 plus 40 plus 600 minus 10x. Well, that would be 850 minus 10x. All right, that's good. So that's our force at any given x. So the way we find work is we integrate our force and from where we start and stop. So in our case, we want to start 0, go up to 30 feet. So 0 to 30, and then it's 850 minus 10x. So we see, all right, well, first two are out because it gets the weight wrong. And between the last two, this one would be if we went all the way up. So the bound is wrong, but of course this one, just right. So the answer is C. All right, good. That's making progress. Number 6. Set up an integral to find the volume which results from rotating the region cosine of x less than or equal to y less than or equal to secant x, and 0 less than or equal to x less than or equal to pi force around the line x equals pi halves. All right, well, what does that do? Well, we have the cosine doing something like this, secant is doing something like this, and we're only going up to pi force, so here's pi force. We're going around x equals pi halves, which is over here, and we're going to rotate. Woo! Okay, so we're taking our region here, and we're going to spin it, and we're going to form some shape. Now, notice that we're integrating in all of these with respect to x. So that says, if I'm integrating with respect to x, it's like I'm taking a small slice, and when I spin, what will I form? I'm going to form a little cylinder. Means we're definitely thinking shell method. Okay, so shell method, we have our integral, start to stop, 2 pi, and then we have our distance, if you like, think of it as our radius, and we have our height, and then there's the thickness of the shell. So the thickness, that's our dx. The height, well, that's between the curves. So secant minus cosine. There's no square. Remember, that's something different. That's if we were doing our disk method. See, this is a red herring. It's trying to distract us. That would be if we're doing disk. Okay, and that's not it. Now notice, so far so good. Everything has a dx, and these three all have secant x minus cosine x. Our bounds, by the way, 0 to pi 4, so that's good. So it's coming down now to this part. So what do we have? 2 pi, and now our radius is from here to there. It's that distance right there. So in other words, we're going to go from our x over to our pi halves. So large minus small, pi over 2 minus x. So if we multiply this through, what do we get? Well, the 2 pi times pi over 2 becomes pi squared, and then 2 pi times x is 2 pi x. And so that's our thing. Now, in some sense, it's a little bit challenging because it says, okay, how do you choose to simplify, right? What's the proper way? So anyways, we're looking for pi squared minus 2 pi x. Now, there's only one of those, so that's the answer. That's it. So it will be, there's a little bit of subtlety in setting stuff up because it says, all right, normally we wouldn't multiply the 2 pi through, but they did that. And so we've got to figure out, well, what did they do so that we can fit into that form? But that's all right. It's fun. A puzzle. A puzzle. All right. Number 7. So we're given f of x equals arctangent of x. And we're asked to find the Taylor expansion up to order 3. So P3 of x. So remember, order just says, how many derivatives do you take into account? It doesn't mean the degree of the polynomial. So it may or may not be a degree 3 polynomial. We'll find out. And then it says, use the resulting polynomial to calculate P3 of 3. Well, what do we have? Now, one thing is we can just explicitly find the Taylor polynomial by saying, all right, we start with the function, and that's arctangent, and we're just going to go for 3 derivatives. So f prime, 1 over 1 plus x squared, which I can write this as 1 plus x squared to the minus 1. F double prime, I can bring the minus 1 down, 1 plus x squared to the minus 2, then I can multiply that by the derivative of the inside, which is 2x. Now, at this point, well, there doesn't seem to be really much advantage here, so I'll just go ahead and write this out. Minus 2x over 1 plus x squared. All right, triple prime. Third derivative, got to go up there, right? Because it's the order 3. Order matters. So let's see, we have the bottom times the derivative of the top minus the top times the derivative of the bottom, which will be 2, 1 plus x squared to the 1. Oops, ran out of space. Times the 2x. Don't forget there's a 2x there. All of that divided by 1 plus x squared, squared. Okay, good. Now, I don't need to clean up because I'm not really going to do anything with the third derivative other than evaluate. So, we evaluate. Arctangent of 0, 0. Plug in 0 into 1 over 1 plus x squared, 1. Plug in 0 to 2x or 1 plus x squared squared. Well, you're not going to recover from that 0 upstairs. All right. How about third derivative? Well, this last term is going to go away because there's a 0 there. The denominator will be 1. And here we get 1 and times a minus 2. So, negative 2. All right, cool. So what does that say? Well, it says that our Taylor polynomial of order 3, in general, it would be, since we're centered at 0, and how does it say centered at 0? We should add that comment. We'll fix this in post-production. Centered at 0. All right, so, well, what is that going to be? We're going to have our f of 0 plus f prime of 0 times x minus 0 plus f double prime of 0 times x minus 0 squared over 2 factorial plus f triple prime of 0 times x minus 0 cubed over 3 factorial. Now, we're going to get 0 and 0, so those terms are gone. Then we're going to get 1 times x, so that's x. Then minus 2 times x cubed over 3 factorial, which is 6, or x minus 1/3 x cubed. Okay, so that's our P3, our Taylor polynomial of degree 3, P3 of x. Finally, all right, what do we do? Well, what is P3 of 3? So P3 of 3 is going to equal 3 minus 1/3 times 3 cubed. So that's going to be 3 minus a third times 27, 9, or negative 6. Well, negative 6 is on our list. Now you might be thinking, that doesn't feel very accurate, because if you know anything about arctangent, and hopefully by now you do, it looks something like this. So when I plug in 3, I shouldn't be negative, I should be positive. This seems like a bad estimate. Well, of course it's going to be a bad estimate. You might say, why is it? Of course it's going to be a bad estimate. Well, I will point out, first off, 3 is quite a ways away from 0. And since we're starting at 0, if we're looking at our expansion around 3, that should be a problem. But in general, if you think about the arctangent series, we actually derived this. It turns out that it has the radius of convergence is 1, which means that arctangent's really only going to give you a good estimate from -1 to +1 in terms of value. And anything outside of that is just absolutely terrible and atrocious. So, well, that's all right. On a test, works great. Okay, sorry, getting sidetracked. Arctangent has that effect on me. Number 8. You want to approximate the surface area that results from when y equals 1/6x cubed for 0 less than or equal to x less than or equal to 1 is spun around the y-axis. But you're having a hard time carrying out the integral, so decide to use a Taylor polynomial approximation instead. All right, well, that seems reasonable enough for us to do. Okay, and what are we going to do? Well, we're going to have it centered at 0, use 3 non-zero terms. So, what does that really say? We're going to estimate this by integrating some polynomial which has 3 non-zero terms. What polynomial should be used? Now, if you're feeling like, wow, what a problem. I wonder if this is one that Steve wrote. It is. I wrote this one, which makes me nervous. I hope I got one of these is correct. All right, so what do we have? So let's try it out. First off, let's talk about surface area. So surface area is what? Well, integral a to b 2 pi, then you have a radius, and then you have a length. All right, that's not so bad. In our case, a to b, 0 to 1. 2 pi, what's our radius? Well, it depends, where are we spinning? We're spinning around the y-axis. So, if we're thinking about our radius here, we have this curve. Our distance to the y-axis is x. So, x. That's pretty straightforward. What's our length? Well, that's the square root of 1 plus. Now, take the derivative and square. So the derivative of 1/6x cubed would be x squared over 2 and dx. All right, so that's integral 0 to 1 of 2 pi x square root of 1 plus x to the fourth over 4. Well, I get where they're coming from when they say, yeah, we're having a little bit of a challenging time to integrate that. We actually could do it, by the way. It's not impossible, but it's definitely not fun. So, all right. So we said, look, we're going to do a Taylor approximation. Okay. So how are we going to do this? Well, remember, Taylor approximation means polynomial. This part we're happy with. All right. Which means that this is the part that needs work. But this is the right form. See, it's really 1 plus x to the fourth over 4 to the 1/2 power. So this is a binomial series. So what we can do is we can say, look, this is 1 plus power 1/2, choose 1, times x to the fourth over 4 plus 1/2, choose 2, x to the fourth over 4 squared, plus other stuff. But I only need 3 terms. Now remember, binomial series, we'll go ahead and write that down. That says 1 plus z to the alpha, that's the summation of alpha, choose k, z to the k. So that's what we're using there. So a half choose 1 is a half. Well, think of it as a half over 1. A half choose 2 is a half times negative a half over 2 times 1, which makes this minus 1/8. So it's 1 plus 1/2 times, there's a 4 here, so 1/8 x to the fourth. And here you get a minus 1/8. And then there's another 16 there. Wow. 8 times 16. Well, what is that? That's 128, I think. Yeah, that sounds believable. So 1 over 128, x to the 8. All right, so that's that term. Don't forget there's a 2 pi x. Okay, now, well, what do we need to do? Well, the last thing is we need to multiply through. So we should have a 2 pi x in the front. Okay, that rules those out. The next term, 2 pi x times 1/8 x to the fourth. So that would be, well, pi over 4 x to the fifth. And, well, that rules that one and that one out, but that has a pi over 4 x to the fifth. So our answer better be C. And just to finish it off, let's see, 2 pi, 1 over 128. Yeah, that does end up with being 64. And then x to the 8th is x to the 9th. So C is our correct answer. If this problem makes you nervous, you should know that we did not pick the hard problems for the final. We picked the interesting problems. But oftentimes we said, well, what's a reasonable problem and what's an unreasonable problem? And given 2 choices, we would say, well, we'll put the challenging, unreasonable ones on the practice just to get people to study. But you know what? On the real exam, we'll give them the fun, interesting ones. So don't get too nervous. Don't get too nervous. Get the right amount of nervous, but just not too nervous. Number 9. Find whether the sum 1 to infinity of 3 to the n plus cosine squared over 5n squared over 4 to the n minus sine squared over n factorial converges, diverges, or is inconclusive by doing a limit comparison test. Well, they'll never know what test we use. They're just suggesting, hey, here's a test for you. We don't have to do limit comparison. But really, what does limit comparison say? It says, get rid of the noise. What's our noise? Well, whenever you have plus or minus, you ask, what matters? So here, we can say, look, in the 2 terms, the 3 to the n is getting huge. Cosine squared never gets big. It's always somewhere between 0 and 1. Same thing downstairs. 4 to the n gets big. Sine squared of n factorial, even though n factorial is huge, sine squared of n factorial never gets bigger than 1. So that's small too. So what we have is really saying, look, get rid of the small stuff. It really looks like 3 to the n over 4 to the n, or 3/4 to the n. So that's really what it behaves like. So this is our behavior. The rest of it's just noise. Now the question is, the sum of 3/4 to the n, does this converge or diverge? And this converges, and we don't need to justify it, but we need to know, if we want to test, why does it converge? It's geometric. It's geometric, and it's the case that 3/4 is less than 1. True story. I learned that a long time ago, and therefore it's a converging series. All right. Oftentimes if you see cosines and sines showing up, what does that mean? Well, it means either there's a hidden plus minus 1, or it means that there's something to be ignored. Okay, number 10. From the list below, select all the series which converge. Okay, so we're trying to figure out what converges and what diverges. Now the nice thing is we don't have to justify anything, and therefore we can go through this pretty quickly. So what do we have? A couple of these are easy to spot. Notice here, log of root n, this gets big eventually. So this is above 1 over root n. Well, 1 over root n, that's a p-series, that's going to diverge. Similar process, this is getting big, so this is definitely going to be bigger than 1 over n. That's going to diverge as well. Easy enough. Here, you see that there's a power, so this is really a geometric. So what you have is, this is really like 1 over root 3 to the n. And 1 over root 3 is less than 1. And therefore, geometric series, this is going to converge. All right, so that's on our list. All right, so those are done. Now the last one. The last one. Well, what do we have? It's really n over e to the n. Now, this one maybe is not immediately obvious, but it turns out we've done this one before. There's a couple ways you can do this. One is you can just recall. It turns out it does converge. What could we do? Well, one way to justify is we could do an integral test and say, what about integral of x e to the minus x from 1 to infinity? And, well, if you work this integral out, what would it be? All right, you're going to make me actually do it? Okay. It's going to be minus x, e to the minus x, and what else will we need? I think we'll need a minus e to the minus x. And, yep, okay, that's the integral. It's not so hard to work out. Just do our integration by parts. Now, you don't care what happens at 1, but the important thing here is that the e to the minus x is going to definitely be tiny. In fact, it's so small that even when you're multiplying by x, the whole thing goes to 0, and so this converges. So you can do an integral test, or you can say, hey, we actually did this series before, the sum of n x to the n. We know that converges if the size of x is smaller than 1. So that is also converging. All right, good. Okay. Number 11. Find the coefficient for x cubed in this convolution. Now, convolution is a fancy way of saying we're going to multiply. So we're taking these two series and we're going to multiply them out. And then at the end we want the coefficient of x cubed. So the way you can do it is, let's just write out the series. So we start here, negative 1 to the n, x to the n. So we're going to end up with a 1 as the first term, minus x, plus x squared, minus x cubed. And then everything else I don't need to worry about, because everything else won't have any effect on the x cubed. You only need to go up as high as whatever power you're looking for. Now here, what happens? Well, when you're 0, you get 0. When you're 1, you're going to get 1 times 2 to the 2. Okay, well, what's that? That's 4. So 4x. Then 2. So that would be 2 times 2 cubed. Well, that's 16. So 16x squared. 3. That'll be 3 times 2 to the 4. Well, that's 3 times 16. That's 48 x cubed. And then, dot, dot, dot. We don't need to worry about the higher powers. So what happens next is we say, look, how can we get an x cubed? Well, you can take the 1 from the first times the x cubed, the x times the x squared, or the x squared times the x. Those are the only ways we can multiply and get an x cubed. So what are our coefficients? We have a 1 times 48, a minus 1 times 16, and a 1 times a 4. So 48 subtract 16 would give us 32, plus 4 gives us 36. And there you go. So whenever you're asking to find a convolution, it really just means multiply things together and figure out what the term should be. All right, good. Number 12. Select the function or functions which correspond with the integral dx over square root of 4a squared plus 4x squared. Okay, now that's interesting. Functions plural? Wait, what? We're going to have to think about that for a second. How could we possibly have more than one function? Oh, good question, good question. Well, let's see. What can we do? Well, first off, the 4 is common. You can pull it all the way out. So that's like we have a half integral dx over square root of a squared plus x squared. Now, one thing we could do is take these derivatives. They do not look like nice derivatives. And so we're not going to do that. Sorry, I know you're probably like, man, but I really wanted to do that. Okay, so what are we going to do? Well, let's actually think of the process. So what do we have? Well, if we have a squared minus x squared, our substitution would be to use our sign. If we had x squared minus a squared, our substitution would be secant, but we don't have those. We have a squared plus x squared, so our substitution is tangent. So dx would be a secant squared theta d theta, and the square root of a squared plus x squared. Well, there's going to be a squared on both terms, so that comes out. Then you have 1 plus tangent squared, which is secant squared, and then that becomes secant. So we get 1/2 integral a secant squared theta d theta over a secant theta. The a's cancel. I can cancel off a secant. So I just have the integral of secant, which is, of course, we have it all memorized. Say it together. All right, good. 1/2 from here, log secant plus tangent. Now, from there, and of course we need a plus c, but they all have plus c. So that's, if one of them was missing a plus c, that's an easy knock it out. Cool. So, what can we say? Well, we know what secant is. We know what tangent is. Tangent is x over a. So that's x over a. Do we know secant? Well, actually we do. See, secant theta times a, that's the square root of a squared plus x squared. So that's the square root of a squared plus x squared over a. So our answer is 1/2 log. Now we wrote ln, but you can also write log. They're the same function. And square root a squared plus x squared plus x all over a plus c. Aha! C. And good. We're done, right? Wait. Let's be careful. Let's be careful. Is there anything else that has a potential to work? Now, B and D, they have a 1/4 when we have a half. So those aren't. But what about A? Could A also work? Well, the difference is that this has this sort of piece downstairs. Now here's the thing to keep track of. See, a is a constant. So this is the same as 1/2 natural log of square root of a squared plus x squared plus x minus 1/2 natural log of a, because I can subtract the division plus c. But now I can make this a bigger c. In other words, it's a constant. So it turns out that's also a solution. So there's multiple solutions. Now what's the difference? The difference boils down to saying, hey, these c's don't have to be the same. They can be slightly different. And so it's a shift from one another. Now, you should always be careful about questions like this. And okay, it's a little bit of a subtlety, but whenever you see an option that, multiple things can be selected, keep in mind there might be multiple correct answers. And if there are multiple correct answers, you want to make sure you get them all. Remember, channel your inner Pokemon. You got to get them all. Okay. So that puts us at halfway. We're doing great. We're doing wonderful. Okay, number 13. The region shaded below, this piece right here, is given by which of the following? Now the nice thing is we can see 0 in all of these, and we also see a cosine 3 theta in all of them, so good. So we just got to figure out, well, which one of these is right? So, what can we say? Well, this one is kind of interesting because it says cosine 3 theta is less than or equal to r is less than or equal to 0. Well, that implies that the cosine is negative. And what else we have? We have pi over 6 to pi over 2. All right. Well, what is that? Well, one of the things you might find useful, when does cosine 3 theta equal 0? Well, when does cosine equal 0? That's at pi over 2, 3 pi over 2. Then at, what's next? 5 pi over 2, 7 pi over 2, 9 pi over 2. Is that enough? We'll throw in 11 pi over 2, just for good measure. So that says our angles are at pi 6, pi halves, 5 pi 6, 7 pi 6, 3 pi halves, and 11 pi 6. So we have sort of these angles here. So this is at pi 6, pi halves. Here's our 5 pi 6. Then we have our 7 pi 6, our 3 pi halves, and our 11 pi 6. All right. Now, we see, where's our leaf at? Well, it seems to be over here, between 7 pi 6 and 3 pi halves. Now, the thing is, that's not one of our options. That's a little bit disconcerting here. Well, what could be true though? Well, here's the fun thing. It could also be over here. Now you might say, no, it's on the other side. Well, right. See, if I'm between pi 6 and pi halves, and r is negative, I'd end up over here. So is there anything that goes between pi 6 and pi halves? Well, there is. That's right there. Okay. Now, the only thing we should sort of convince ourselves of is what's true about the cosine. Is it negative in this range? Well, the answer is yes. Now, that doesn't sound very convincing just to say that. You can plug in a value. Pick something between pi 6 and pi halves. Say pi thirds. That's between pi 6 and pi halves. Cosine of 3 times pi thirds is cosine of pi, which means it's negative. So I am over here. And so, going by, just like what range for theta do I need in order for this to work, we can say it must be A. A is the only possible range where it could work. And the others we can say, look, it couldn't work. 0 to pi halves, well, that says you'd have to include this piece here as well, because that's where we're at from 0 to pi halves. Pi halves to 5 pi 6, you'd either be over here or you'd be down there. That's not going to work. Pi 6 to pi thirds, well, that would be, if you were in here. And that's not going to work. So yeah, well, it's just saying what's the right range, or what's the possible range for theta that could fit the picture. That's what you get. All right, number 14. Applying integration by parts once to the integral of x cubed arctangent of x dx gives which of the following? All right, so we're not going to go all the way. We're only going to take our first step. So, See, this is a time when if you put it into a calculator wouldn't help you, because it would say, oh, here's the final answer. You're like, whoa, slow down. I need to see the first step. And the calculator says, no. We're going to give you the whole answer. So don't use calculators. Use your own abilities, because you're good. You're really good. All right. So, well, look, if you were asked to integrate x cubed arctangent of x, there's two pieces. There's the x cubed and the arctangent. Now, between these two, arctangent, you don't want to integrate that because it doesn't have a great integral. And if you were to integrate arctangent, you'd have to do integration by parts. So that seems to sort of defeat the purpose. But great derivative. So we're going to make that the part we take a derivative of. This is the part we integrate. So we have v, the integral of x cubed is 1/4 x to the fourth. And then our derivative of arctangent, du, 1 over 1 plus x squared dx. So we should have uv. So 1/4 x to the fourth arctangent of x. And, okay, I see that. All right, so that rules out those two. Now, what's the difference? One of them has a plus c, one of them has another piece. Well, remember, integration by parts, it's uv minus the integral of v du. So minus the integral 1/4 x to the fourth, 1 over 1 plus x squared dx. See, there's another integral here. It's not a plus c. You're not finished yet. The integration by parts really says, I'm going to trade one integral for another integral, and hopefully the other integral is simpler, and it does match with that one. So our answer is B. All right, good. Now, of course, you might say, did they do anything to trick us? Well, yeah. See, here, it's like almost the same, but they took a derivative of 3x squared. Sorry, derivative of x, you would get 3x squared instead of integrating. So you got to pay attention. We kind of know what mistakes you might be thinking of. So we've been doing this for a while, and so pay attention. You'll be fine. You'll be fine. I believe in you. You're good. You're great. Wonderful students. Number 15. Find a value b greater than 0 so that the integral from 0 to infinity of x divided by 1 plus bx squared squared is equal to 5. And this one is not multiple choice. Submit as a number, rounded to the nearest hundredth. Okay, cool. So we're going to have to figure out what could this possibly be. All right. Well, how could we integrate this? Well, so we have that 5 is equal to 0 to infinity x over 1 plus bx squared dx. Well, it looks like a good candidate for substitution. And namely, we can say, well, the inside is this part here. So we'll make this u. U is 1 plus bx squared. Du, the root of that, 2bx dx. And I'll move the 2b across. So 1 over 2b du is x dx. So, what do we get? Well, we get that this is equal to 1 over 2b. All right, that's coming from here. That's the x dx. Integral. All right. Then we have our du. And 1 over u squared. Okay, so the x dx is the 1 over 2b du. This 1 plus bx squared is u squared. So, all right. What about our bounds? Okay, got to pay attention. Plug in 0. 1 plus b times 0 squared, 0. Plug in infinity. Well, you can't plug in infinity, but what happens as you go to infinity? What happens is this is going to get huge. And so we're going to infinity. Now this is an integral we can actually do. Plug in 0, you don't get 0. You get 1. 1 plus 0. So, sorry about that. 1 over 2b. It's always good to check your work. You've got the time. There's no time limit. You can finish the test and then go back and check your work. You can have plenty of time. So, what is that? Well, you add 1 to the exponent, so that's going to be u to the minus 1, divided by the new exponent. Well, same as multiplying by negative 1. We're going from 1 to infinity. The nice thing is, as we go to infinity, because this is a negative exponent, we're going to get 0. Subtract, when we plug in 1, you get 1. So, minus 1 over 2b. Or, you get 1 over 2b. So, cool. So remember that equals 5. So, now let's flip both sides. 2b equals 1/5, b equals 1/10. Well, we got to submit it as a number, round to the nearest hundredth. So that would be 0.1. And I guess we could add 0. 0.10. Done. Good. That's the answer. All right. Number 16. A wire with constant density 1 has been bent into the shape of a parametric curve. T plus sine of 3t, comma cosine 2t, where t goes from 0 to pi. Select the integral which computes the inertia of the wire with respect to the x-axis. And our first reaction is like, what? Now, remember, how does inertia work? Inertia, I'm going to feel like I'm talking a little bit too much physics here. I didn't really take physics, so you add up, and what you have is inertia is your distance squared times your mass. Now, how do you find distance squared? Well, we're going to the x-axis. So if I want to go to the x-axis, your distance here is your y. In our case, what are we integrating? Well, our bounds are by time, 0 to pi. Our distance, that's our y, that's cosine 2t, and we need to square that, so cosine squared of 2t. Okay, so we can already start to say, these are not looking promising. These look promising because you have a cosine squared of 2t. Now, how do you find mass? Well, mass is going to be density times, in our case, a wire is length. So really, here, we're going to take it 1 times our length. So how do you find length? Well, it's going to be the square root of, and I'll write now for x prime squared plus y prime squared dt. There's also 1 times, but okay, that's fine. So what I need to do is I need to take the derivative. So the derivative of x would be 1 plus 3 cosine 3t. Derivative of y would be 2 sine 2t, actually negative, but I'm squaring it, so it doesn't matter. So you notice this is just x and y, this is x prime and y prime. So that says it's f, because this is the right form for length. This is length. Here, this is not length. And so we're good. That's the answer. Now, in general, how do you do problems with wires? It's not so bad. You just think about, okay, really I think of my little pieces as little bits of length. So I can talk about a mass times a length, and I can do, well, pretty much that's all I need to do, right? I could have a density which varies with t, and then I could have something more interesting here than just 1. But, you know, that's it's all fun. Good. 2/3 of the way there. All right. 17. Find the tangent to the parametric curve x equals secant t, y equals tangent t, t going from negative pi halves to pi halves when t equals pi fourths. So, what do we get? Well, I need a tangent, really a tangent line. So, where's our line? Well, plug in pi fourths. So, our point would be secant of pi fourths, tangent of pi fourths, and it looks like they don't have secant pi fourths, tangent pi fourths. We've got to actually compute these things. Secant of pi fourths is square root of 2, tangent of pi fourths is 1. Now, we can actually use that to throw out some possibilities. That says, if I plug in x equals square root of 2, y has to be 1. So, square root of 2 times square root of 2 is 2 minus 1. Okay, that's possible. 1 over square root of 2 times square root of 2 is 2. Sorry, is 1. The square root of 2 is canceled, minus 1 is 0. So that can't work. If I add square root of 2 plus pi fourths, that's not 1. That can't work. If I have minus root 2, minus root 2, that can't work. And so just by the point, we can eliminate 3 of the possibilities. So we know it's either y equals root 2x minus 1 or none of them. So good. We have a 50-50 chance. All right. I'm kind of hoping it's A. I don't like it when it's none of the above. I had a friend once who I was helping him teach his class. And, he always put on none of the above on every problem, just in case. Well, one semester he didn't pay very good attention, and 2/3 of the problems were none of the above. You got to be very brave to keep circling none of the above. But, well, there were some brave students. Okay, so how do we finish it? Well, we need the slope. So how do you do the slope? Well, that's change in y, or y prime, over change in x, x prime. Derivative of y, well, derivative of tangent is secant squared. Derivative of x, derivative of secant is secant tangent. And of course you can say, well, look, that's really secant of t divided by tangent of t. Now, because I can cancel off a secant, so at pi fourths, what do we get? Well, we're going to get secant of pi fourths divided by tangent of pi fourths, which is root 2 over 1, which is root 2. So our slope has to be root 2. That is the slope of this line. And so, right point, right slope, that's our answer. A. Nice! Woohoo! Number 18. Find the integral sine squared of x cosine squared of x dx. And there's a bunch of choices here. They all have the plus c. So, if none of them had the plus c, that would have saved us a little bit of work, because we can say, aha, it has to have a plus c. It's indefinite. Now, one of the things we can do is we can sort of say, what if we try to go backwards and take the derivatives of these and say, do they match? Well, the problem is, if you take the derivatives, they're not going to look like sine squared cosine squared. They're going to look like some expression which does not look like sine squared cosine squared. It's going to have sine of 2x's or sine of 4x's involved. So I don't think it's going to actually save you any time to say, well, let me work from the answer backwards. So what can we do? Well, what we can do is work on power reduction, because everything is even powers. Now, in our case here, this is sines and cosines. My favorite way to do this would be saying, look, this is really the same as 2 sine x cosine x divided by 2 squared. Now, why do I like that? Well, because I like to use the sine 2x identity whenever I can. So, this is the same thing as sine squared of 2x over 4. Now, you don't have to do this, but this is certainly, it's a valid way to approach it. All right, now, okay, what can you do next? Well, sine squared, there's a power reduction for that. So sine squared is 1 minus cosine, double the angle, if it was 2x, it's now 4x, and divide by 2. So the 1/4, and then sine squared. So the 1/4 and the half is really 1/8. Now you integrate each piece. The integral of 1 is x. The integral of cosine is sine. So since it was minus cosine, it's minus sine. 4x on the inside, and then divide by 4, plus c. So that's 1/8 x, and 8 times 4, 1/32, sine of 4x plus c. And there we are. It's A. Good. Now, you might ask, is it one of the others as well? Because, trig identities are tricky. And this is a case when it's multiple choice, not multiple select. So you only have to worry about multiple correct answers if there is the option that you can choose multiple answers. If there's not, then you don't have to worry that, aha, there's a secret hidden one. So we're okay. We're done. Number 19. Which of the following integrals calculates the length of the arc y equals e to the 3x for y going from 1 to 27? And notice here, select all that apply. Now, again, this is an indication you might have the possibility of multiple correct answers. So, well, let's see. How can we have multiple correct answers? Now, we know how to compute length of a form y equals a function of x. That's the integral a to b, the square root of 1 plus y prime squared dx. Normally we write f prime of x, but same idea. So we say, okay, well for us, let's say 1 to 27, square root of 1 plus the derivative of e to the 3x would be 3e to the 3x squared dx. So what does that turn out to be? Well, that's the integral 1 to 27 of the square root of 1 plus 9e to the 3x quantity squared would be 6x dx. Now, is that an option? Ooh, tempting, but notice, be careful, that 9 does not match that 6. Okay, which means close, but no cigar. Okay, all right. By the way, I don't endorse using cigars. It's just an expression. And, all right, well, that's not good. That's not good at all. Well, notice here we do have a e to the 6x. Well, was that our right answer? And then looking back, we say, oh, wait a second. I see. I screwed up. See, because it's 1 to 27 for y, not for x. Good thing I double checked, right? Okay, well, what is that? Well, for what values of x gives us these values for y? So when does 1 equal e to the 3x? Well, that happens at x equals 0. So that would be 0. Well, when does 27 equal e to the power 3x? By the way, 27 is the same as 3 cubed. Take the log of both sides, you get 3 log 3 equals 3x, or log 3. So it really should be 0 to log 3. 0 to log 3. And that's what we have, 0 to log 3. Good. All right. So our answer is D, right? Maybe. But we haven't ruled out these options as well. So this is sort of integrating with respect to x. How about with respect to y? Well, now, building off of my screw up from a few moments ago, look, here, these are x bounds, so that's not going to work if I'm integrating with respect to y. This is a possibility, though. So what would that be? So that would be saying what? Well, if I integrated 1 to 27 dy, but now I have to be careful here. It'd be the square root of 1 plus something squared. What goes here? Well, take your expression, solve for x. So we get natural log of y equals 3x, or x equals natural log of y over 3. Take the derivative with respect to y. And if you do that, well, you get 1 over 3y. So 1 to 27, square root of 1 plus 1 over 9y squared dy. That's the answer for A. So, both A and D are correct. What? Cool. Cool. Good times. Good times. All right. Number 20. Find the exact value for the sum 1 to infinity 6 over n squared plus 3n plus 2. And submit answer as a number rounded to the nearest hundredth. Again, I should add, we're going to see a couple problems on the exam where you have to submit answers rounded to the nearest something. They're always going to be nice numbers. They're going to be easy numbers to work with. So, what do we have? Well, there's only a couple of things we can do where we're looking for exact value. Geometric, telescoping, Taylor. We mentioned those before. It's not geometric, powers of n. Taylor, about the only thing that we really see for Taylor is if we have something where we have factorials involved, or maybe some powers n squared. This is a little bit more complicated. But one thing we definitely have is we say, hey, this is a polynomial and it factors. Factors as n plus 1 times n plus 2. So what we can do is we can do our partial fractions. Something over n plus 1, something over n plus 2. Clear our denominators. 6 equals a times n plus 2 plus b times n plus 1. Plug in n equals, say, negative 1. And what do we get? We get 6 equals a. Oh, that was easy. All right, plug in n equals negative 2. We'll get 6 equals negative b, or b equals negative 6. So what we have is really, this becomes the sum from 1 to infinity of, we have 6 over n plus 1, subtract 6 over n plus 2. And this is a telescoping sum, because these are similar expressions, just shifted off by 1. So if we start writing things down, and a key thing here is that these go to 0. Since they go to 0, that means you only need to say what doesn't cancel at the start. Whatever doesn't cancel at the start is going to tell you what your sum becomes. So you have 6 over 2 minus 6 over 3. That's your first term. Plus, the next term, 6 over 3 minus 6 over 4. Plus 6 over 4 minus 6 over 5, and so forth and so on. But you see that the terms are going to cascade. They're going to cancel off. Again, because the terms at the end are going to 0, the only thing that doesn't cancel is the term up front, so the answer is 3. If we round that to the nearest hundredth, 3.00. And there's the answer. Woohoo! Fun. All right. 21. Consider the power series, negative 1 to the n, x plus 2 to the n, divided by 5n over times log n. Okay? What is the center of the interval of convergence? Round. Submit as an answer round to the nearest hundredth. Okay. Well, if you're doing the center, you're looking at this piece that involves the x. See the x plus 2? And then you say, all right, what would make that 0? So in other words, which values of x you choose so that x plus 2 equals 0? Well, the answer is negative 2. round it to the nearest hundredth, negative 2.00. All right, that's easy enough. Radius of convergence? Well, if we're going to do radius of convergence, what we should do is probably do a root test, because we see lots of powers here. So we're going to take a look at the limit as n goes to infinity of the absolute value, negative 1 to the n, x plus 2 to the n, over 5 to the n, log of n to the power of 1 over n. Now the absolute value says, don't need to worry about that alternating part. So this becomes absolute value of x plus 2 over 5. And then there's this last piece, the limit as n goes to infinity of 1 over log of n to the 1 over n power. And you can either know facts or just reason. And here, this part is going to go to 1. So that says you have x plus 2 over 5 is the limit, and this will converge if this is less than 1, or if absolute value of x plus 2 is less than 5, and that's your radius. So our radius is 5, rounded to the nearest hundredth would be 5.00. All right. All right. Number 22. Oh, an arctangent problem. This one's got to be good. So we're given that f of x equals arctangent of x e to the x, and we're asked to find the fifth derivative at 0. Now, a Calc 1 approach would say, hey, let's take 5 derivatives and life will be good. But we're not Calc 1. We want to do something smarter than Calc 1. Well, what's smarter? Well, what's smarter is to say, look, if I'm looking for something about derivatives, think Taylor series. That's source derivatives. We know Taylor series for e to the x. That's the sum, 0 to infinity, of x to k over k factorial. Now, how about arctangent of x? Do we know that one? Well, maybe. Now, it depends. You might have it written down in your notes, and maybe you're like me and you just love arctangent so much you have it memorized. But if not, you can rederive it really quick. You know that derivative of arctangent is 1 over 1 plus x squared. That's 1 over 1 minus x squared, which geometric series, that's the sum, 0 to infinity of minus x squared to the k, or sum 0 to infinity minus 1 to the k, x to the 2k. All right, that's the derivative. So you integrate, you get that arctangent of x is equal to the sum from 0 to infinity of minus 1 to the k, x to the 2k plus 1 over 2k plus 1. Now technically there's a plus c, but since arctangent 0 is 0, c goes away. All right, so we know our two pieces here. So sum 0 to infinity minus 1 to the k, x to the power 2k plus 1 over 2k plus 1. The other thing we know, and this is sort of an important idea, is to say, look, I have that f of x in general is the sum 0 to infinity, the kth derivative at 0 over k factorial x to the k. So what are we after? Well, we're after the fifth derivative of 0. And so we say, well, if I want the fifth derivative of 0, I want k equals 5. So the coefficient of x to fifth is the fifth derivative at 0 over 5 factorial. So we can say, let's try to find the coefficient of x to the fifth. So where are we at? Well, let's take our two series. We have our first series starts off as x minus x cubed over 3 plus x to 5 over 5 and other stuff. So this is our arctangent. The other stuff we don't need because it's going to go away. In other words, why do I say it goes away? Well, it doesn't contribute to the coefficient of x to the fifth. Now, e to the x, that's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, which is 6, x to the fourth over 4 factorial, which is 24, x to the 5th over 5 factorial, which is 120, and other stuff. Now, if I want to end up with x to the 5th, I say, okay, how can I get it? Well, I have x, I can multiply that by x to the 4th. X cubed, I can multiply that by an x squared. X to the 5th, I can multiply that by a constant. So I can get it in 3 ways. So in particular, I can say the following. Well, the coefficient of x to the 5th, that is the 5th derivative at 0 over 5 factorial, which is this fact here. And it is also, let's see, 1 times 1 over 24, so that's 1 over 24, minus 1 over 3 times 1 over 2, so that's minus 1 over 6, and 1 over 5 times 1. Now, the 5 factorial, I'm going to multiply both sides by 5 factorial, which, by the way, is 120. It's the same thing as right here. 24 goes into 120. That leaves us 5. 6 goes into 120. That's 20. 5 goes into 120 as 24. 5 plus 24 is 29. Subtract 20 leaves us with 9. Aha! There we go. Hey, what a problem. Eh? All right. 23. Determine whether the series, the sum 0 to infinity, sine of n plus a half pi over 1 plus root n, diverges, converges absolutely, or converges conditionally. Now, the sign upstairs, well, we've got to think about how to deal with that. Well, how do we deal with that? Good question. Well, let's just think of the first couple of terms. So, at 0, 0 plus a half would be sine of a half pi. So, that's 1. At 1, 1 plus half is 3 halves. 3 halves pi is negative 1. How about at 2? 2 plus a half pi, that's 5 halves pi. It's back to 1. So what's going to happen is it's really alternating, plus 1, minus 1, plus 1, minus 1, so forth and so on. So that's really just sort of a clever, or maybe not so clever, depending upon how you look at it, way to say, look, it's really an alternating series. Now, alternating, does it go to 0? Well, the denominator gets big, and so, yeah, it's going to converge. Okay, so we can throw out the diverge. Now, the question is, do you need the alternating? Well, let's throw out the alternating. 0 to infinity of 1 over 1 plus root n. Well, let's compare. 1 over 1 plus root n, really, we can do it by limit comparison with 1 over root n, because these have the same growth, and the same dominating terms. This diverges. Why? It's a p-series. It's a p-series where n equals a half. Sorry, not n equals a half, p equals a half. So that's a diverging period series, which means we do need the alternating. So it doesn't converge absolutely, it must converge conditionally. I like alternating series problems. They're kind of fun because, you get to alternate. All right, last problem. So sad to come to the end, but, well, all good things must end, including our last review. Well, so what do we have? The area of the surface of revolution formed by revolving the graph f of x equals x plus 1 from 0 to 1 about the x-axis is which of the following? So we have a couple of choices. Well, they all have pi's. Okay, so that's not going to be it. So what's surface area? Well, it's the integral a to b 2 pi. Then you have your radius. And then you have your length. All right, so in our case, 0 to 1, 2 pi. Now we're going to the x-axis. So if I have this curve x plus 1, and I want to go down to the x-axis, well, that distance is x plus 1. So x plus 1, the length would be the square root of 1 plus the derivative and squared. Well, that's a constant. So what do we have? Well, 2 pi square root of 2, those are constants, so those come out in front. So then you just have to integrate x plus 1, which is 1/2 x squared plus x. Evaluate that from 0 to 1. So we get 2 pi square root of 2, 1/2 plus 1. Well, that's really 2 pi square root of 2 times 3/2. 2's go away. So 3 pi root 2. Aha! We have one of those. That must be our correct answer then. All right, our last one. We made it. Woohoo! All right, I know on some of these I went quick and I could have added more details, but if you go back and watch the old reviews, there are old reviews, there's lots of details out there. So I'll let you search through the details, and of course you can email instructors and ask questions. Good luck. Thanks for hanging in there. Thanks for being part of the class, and I hope you enjoy the test. We want to leave you having a hopefully good experience. And I know some of the questions here have been challenging, and even some of the questions on the test will be challenged, but we only challenge the people we love. If we didn't love you, we wouldn't challenge you so much. So with lots of love, good luck on the exam. All right. Bye.